This is a proton. It is made up of 3 quarks. Now we will place these 3 quarks and the proton on either side of a balance scale. Strangely, the mass of the proton is 100 times heavier than these 3 quarks. How should we understand this phenomenon? There are 4 fundamental forces in our universe. One is gravity. It keeps us firmly bound to the surface of the Earth. One is the weak force. It is related to particle radiation, and one is electromagnetic force. One is electromagnetic force. It is related to the chemical reactions between matter. And there is another, the strong force. It can hold protons and neutrons together in the atomic nucleus, tightly bonded together. Of these 4 forces, you might be most familiar with gravity. At the scale of the Earth and the solar system, gravity dominates the universe. However, on the quantum scale, the other 3 forces play a dominant role. For example, in the quantum scale, the electromagnetic force is 10 times stronger than gravity. The electromagnetic force can allow negatively charged electrons surrounding the positively charged atom. You might wonder, since the electromagnetic force is so strong, then multiple protons in the atomic nucleus should strongly repel each other. In fact, the repulsive force between the 2 protons in a helium atom is about 20 pounds. For something as small as a helium atom, this is undoubtedly a huge repulsive force. The protons should instantly move apart. The reason these protons do not separate is that they are held together by a fundamental force called the strong force. That keeps them stuck together. This force is even 100 times stronger than the electromagnetic force. It is the strongest force in the universe. You may not have felt how strong the strong force is, but I believe you have seen the power of a nuclear explosion. The immense energy released by a nuclear explosion comes from the binding energy that keeps protons and neutrons together within the atomic nucleus. And this binding energy is produced by the strong force. Contrary to what most people imagine, 99% of the mass of matter comes from the strong force. Only about 1% of the mass of matter is rest mass. The strong force not only binds protons and neutrons tightly together in the atomic nucleus, it also binds the quarks that make up the protons. To visually represent the strong force between quarks, we can connect quarks with a spring. When we weigh these 3 quarks, we are actually only accounting for the quark's rest mass, while 99% of the proton's mass comes from the strong force. When we also include the strong force between the 3 quarks in the calculation, the mass of these 3 quarks becomes equal to the mass of the proton.